All right, I think we can start now. Good afternoon and welcome to this presentation. My name is Indrajit Poddar, IP. I'm from IBM Systems, and I have with me Animesh Trivedi. He's from IBM Research, from the Zurich Research Lab. And today we're going to be talking about how, if you're using Apache Spark in Hortonworks, and if you're doing machine learning and deep learning, what can a modern system with its set of optimizations do for your workload? How can you speed up your Apache Spark machine learning and deep learning workloads on a modern platform? And I'll tell you more about what we mean by a modern open platform. This talk was originally scheduled to be given by Raj Krishnamurthy. He's my colleague in IBM Systems Performs, but he could not be here today. So we are presenting in his place, and I'm happy to take questions from you for the Spark optimization section, which is originally his section, and we can get it answered for you offline through emails. So in the agenda today, first we will level set. We're going to talk about Spark, what is Spark and what is machine learning and what is deep learning. We had a very fun session, I thought, this morning in the keynote about how to make technology disappear, and that had a lot to do with deep learning. So I'm going to talk a little bit more about deep learning. Then I'm going to talk to you about Open Power, which is really an open source for, what I'd like to think about it is it's open source for the hardware. And it's an open community. I'm going to talk to you about what Open Power can do for you. And then we're going to talk about 3 types of system optimizations that help with workloads that run on these open power systems. The first kind is these deep learning workloads, and we're going to show you how deep learning with open power systems and GPUs can bring you faster training times. Then we're going to talk about Spark machine learning performance, again, but with only CPUs and with open power CPUs, which are based on the Power 8 architecture, how unique characteristics of the CPU can help you optimize your workload. And the third part of the session will talk, Animesh will talk more about I/O optimization, more specifically about the network, and how that can help you further improve your system performance for your workload. So first, to level set, Spark, I think most of you are aware, it's in-memory analytics, interactive and batch style of analytics. And there are many libraries that are included within Spark. In particular, I'm going to talk about the MLlib, which is the machine learning library. And particularly, its in-memory design is already meant for giving you better performance and faster training times and more bigger analysis of more data. And when we take into account the system improvements that can help Spark workloads, you get even faster results when you're training or you're doing inference with Spark on our systems. So we're going to talk about machine learning and deep learning. And in this slide, you're going to see a number of different pictures of bicycles. And no points for guessing. It's very easy for us, human eyes, to see what is in the picture and to make and say that it's a bicycle. But it's difficult for machines to do the same thing. But now that's changing with machine learning and deep learning. They're learning the way that human brains learn, and particularly by using these neural networks, which mimic the style of learning that human brains do with its neurons and synapses. So the problem that we see now is that when you're doing training, you actually need a lot of computational resources. And as Spark practitioners, I think many of you would try to address this by scaling it out. And it's easy to scale out, and you can do real-time analytics with Spark. You can use Docker, you can use Kubernetes and Mesos. But even with all of that scale out, when you're talking about data, lots of data, images, high-resolution images, and you're talking about video input, and you're talking about billions of features, training on that large size is really time-consuming. It can often take up to hours, days, or weeks. And as a data scientist, it's difficult for you to iterate over models that you design, and train on data. And further, we are seeing that CPUs are not really getting as fast, as rapidly as before. Moore's law is dying. And so what we see here in the systems part of our organization is that there's a need for whole system optimization. That you need to take into consideration not only the CPU speed, but also bring in offloaded computation where you take some of your time-consuming parts of the workload and you offload those into accelerators like GPUs. And then you also have to take into account your I/O performance, and I have some examples of why that is important. So this slide talks a little bit about where we see new innovations that are going to come in the hardware space. And you'll see here that we are in 2017 now. In the next few years, the Moore's law price performance curve is going to keep falling, but we are still going to be able to deliver more performance with the help of optimizations that will happen in the accelerator space, in the software stack, in the storage and network space. And this is particularly true because for workloads which are based on unstructured data, and that is what the Spark use case is primarily. So what we've done at IBM is we have started this consortium, this partnership with many hardware vendors in the industry. And we partnered with companies like NVIDIA, who build these accelerators, these coprocessors for GPUs. We partnered with Xilinx for accelerators based on the FPGA architecture. And we have partnered with system integrators like Supermicro, who can put together a system based on these different components from both IBM and these partners. And then we have partnered with public clouds. This is a screenshot from the IBM Software public cloud, and you'll see here in one rack we have a traditional Intel x86 servers and open power servers in the same rack. And many other public clouds like Nimbix are also including our systems, these open power systems, in their infrastructure, and they're offering many different ways of consuming those systems and the workloads running in the systems. Nimbix in particular offers a platform as a service sort of API, so you can build Docker containers and you can launch them in the Nimbix public cloud. And Nimbix attaches a GPU, at least one GPU to each Docker container, and thereby you can get started very rapidly with your deep learning workloads in Nimbix. You just sign up with your credit card. So Google and Rackspace are also our partners. Google has put our stuff in their data centers, and they have put out many software packages like Kubernetes built for the power architecture. And Rackspace is building their own system based on our design. And so we have many different partners that are partnering with us in the hardware space. And that's why we call it the open power ecosystem. And this is how big it is. We have members on all levels of the stack. We have software partners. We have system integrators. We have I/O and storage acceleration partners, boards, chips, SoCs, you name it. There's a lot of innovation happening in the hardware space in this ecosystem. So I'd like to spend a little bit of time talking about the Power 8 architecture, the processor architecture, which is at the core of the open power family of systems, and the unique things about the Power 8 architecture. First of all, we have quite a lot of cores. Not as many as in GPUs, but still for a CPU, we have about 12 cores, and each core has 8 hardware threads. So when you're looking at it from a software perspective, we have up to a total of 96 CPUs that will show up on your Linux system if you look in /proc/CPU. And we have bigger caches, and this helps to improve your analytic workloads. We have accelerators, which are built into the chip for crypto and memory expansion and transactional memory. We have a memory subsystem, which gives us a lot of throughput in memory transfers, and we have a coherent accelerator processor interface called CAPI, which enables you to treat other peripherals like GPUs and their memory as equal partners in the system. So you can program to this interface as a programmer, and you can make sure that your system, your memory is coherent between your main memory and the accelerator's memory. So one of our first systems here is the Minsky box, which we codename Minsky, and SA22LC. This is ready for purchase. And the unique thing about this is the interconnect. So it's a replacement. So we have something called NVLink, and we have our partner NVIDIA's latest Pascal 100 P100 GPUs connected to the main memory and the CPU through this NVLink interconnect. And the unique thing about the NVLink interconnect is that it's a replacement for the traditional PCIe interconnect, and it provides 2.5x faster transfers between CPU and GPU memory. And this, we have found, is a pretty big bottleneck when it comes to running deep learning workloads, and that's why we are designing this new generation interconnect in partnership with NVIDIA. So now we're going to talk about 3 different types of workloads for Spark, and how for each of these workloads we use system optimizations to speed up the performance. First, deep learning, and how you can, as a programmer, without making significant code changes, you can transparently accelerate your code when you use GPUs in the open power systems. So in order to do that, first of all, we are introducing a software distribution called Power AI, which is specifically designed to run on the Minsky box, and it's easily downloadable. It's a Ubuntu package, and it has precompiled binaries for the Power architecture, and takes advantage of the NVLink interconnect, and includes packages such as Caffe, TensorFlow, and Torch, and Theano, and so these commonly used deep learning frameworks are packaged in binary format in the Power AI software download. In addition to the Power AI software package, basically these systems run the Ubuntu operating system. So along with the Ubuntu operating system comes a whole suite of Python open source frameworks, which are often used in deep learning programming. And so we have Jupyter notebooks, Matplotlib, SciPy, Pandas, and OpenCV, and all of those things. And all of those things can work in conjunction with Spark. In particular, I want to point out deep learning for Java. This is a Java set of bindings to these accelerators like GPUs and native libraries provided by NVIDIA. So if you are trying to, if you come from a Java background and you're trying to write deep learning code, it's probably going to be very fast for you to adopt deep learning for Java on top of Spark, and design a neural network and write some neural network code which is transparently optimized. So here's an example. So this is a piece of, it's example from the Caffe framework. And to switch from the CPU mode to the GPU mode, all you have to do is set mode GPU. And all of the CUDA language program that needs to execute on the GPU to do a deep learning classification is automatically executed for you, and the data is transferred automatically to the GPU, and you get your results back a lot faster. So just to see how much faster, you can see very easily for a CPU timing, we got about 3.29 seconds, but when we use a GPU, that goes down to 11.4 milliseconds. And that's about a 250 times speed up. In addition, when you consider these coprocessors like GPUs with CPUs in a cluster, you also have to think about how you can allocate those GPUs to your workloads. And we have enabled GPU support on top of the Mesos scheduler. We are in the process of adding support into the Kubernetes scheduler, and this is a snapshot of excuse me, of a cloud stack that we have enabled on open power. We have open source components like Kubernetes and Mesos. And we also have a family of Spectrum computing products which can help you with scheduling jobs and using GPUs more efficiently in a cluster. And together with Docker containers and Docker management frameworks and deep learning frameworks like TensorFlow and clustering frameworks like Spark, you can very efficiently create a cluster on top of OpenPower and schedule your deep learning jobs in that cluster. And we also have storage products from IBM Spectrum Scale and IBM Cloud Object Storage, and which can work in conjunction with these management components. We also did a benchmark on top of Power AI, which is and TensorFlow, and we found that in terms of the TensorFlow Inception v3 benchmark, we give about a 30% improvement in terms of processing speed in the training time, and measured in terms of number of images processed per second. In terms of price performance, we see a 1.6 times improvement. Our system comes in at about $67,000 with 4 P100 GPUs, compared to an NVIDIA DGX1 system with 8 GPUs, which comes in at $129,000. We see, if you look at the number of the dollar cost for the processing time of number of images per second, for the Inception v3 benchmark, we are about 1.6 times better. And we attribute much of that improvement to the NVLink interconnect, which helps us alleviate the bottleneck of transferring data from the main memory into the GPU memory. So that brings me to the second part of the system optimization discussion. And in this one, we're going to just talk about the CPU itself and what tuning can you do for Spark if you take into consideration unique characteristics of the OpenPower Power 8 CPU. So what we see here is that when you're doing streaming or running SQL on these unstructured data, often you have a number of different threads which are working in parallel, in concurrent mode. And the high number of hardware threads that we have in our CPUs can help to improve the throughput of processing multiple packets in a stream and in different stages of a pipeline in Spark. And it can also help to process multiple rows in a SQL query with these additional threads. For machine learning, we've seen there are a lot of iterative algorithms which work on the same data when you're training a model. And these iterative algorithms can benefit from the large caches that we have and the high memory bandwidth that we offer on our system. And that results in fewer core pipelines and a higher overall, fewer core pipeline stalls and a higher overall throughput. For graph algorithms also, we see that having these large caches in the hardware and the higher memory bandwidth and the higher thread count helps. So, and when we say higher threads, we have this term called simultaneous SMT, simultaneous multiple threads. And these things show up as CPUs if you're logging into the system at the operating system level. And we can go up from, it's flexible, you can configure it. You can either have 4 threads per core, or you can configure it to 2 threads per core. Each of your cores will be weaker. Each of your threads will be a little weaker if you have larger number of threads per core, but you can have more parallelism that way. So we have some examples of how we tune a particular Spark machine learning workload based on the characteristic of the CPU. And we see that when you're using our system, we have to balance the resource utilization to give the most efficient scale-out usage of the resources available in the system. And so my colleague Raj, who is on the performance team, he has this methodology that he describes where he has an approach towards how you can start from, that's what he calls an out-of-the-box performance that you can get without tuning. And you can go and look at these different types of tuning parameters that Spark offers and go from there and tweak these parameters to take the performance of the system from the out-of-the-box form to what he's calling a good enough performance level, and then take it to something that is calling the roof line. That is the most optimal performance that you can expect to see on a particular workload on a particular box. So he has this example where he's taking the alternating least square spaced matrix factorization algorithm that's part of Spark MLlib, and he's using this process of optimizing the tunable parameters in Spark, like the executor instances, the executor cores, the memory that is given to each executor, the shuffle location in manager, and the RDD persistence storage level. And he has two approaches. First, what he calls the top-down approach. So in this approach, you just take the application and look at the default configuration that is available for these tunable parameters. And then he comes up with what is called the out-of-the-box performance level. And this is really the baseline. And then he takes this bottom-up approach where he starts from the system hardware and looks at what are the resources that are available in that particular system, the number of cores, the number of CPU threads, etc., the amount of memory. And then he tunes these default configuration, looking at the type of workload that you have in mind. And then he comes up with these custom tunable parameters and configuration parameters, which leads you to what he's calling the roofline performance level. To give an example, for the ALS, this matrix factorization workload from the Spark Bench suite, which has these different phases. There's a training phase, there's a validation phase, and then there's a prediction phase, as is common with every machine learning algorithm. This is what he comes up with in terms of the different parameters and the different jobs that he thinks that for that particular workload, and how those jobs take the maximum amount of time to run in this system. So out here you would see this is the output from the Spark history server, and it shows you which of the jobs take the most time. The job number 7, that is this one, that is the most time-consuming part. And for the input parameter, he took into consideration a 100 gigabyte data set, which had 62,000 rows in the matrix and 62,000 columns. And these were the default configurations that he chose for Spark. First, he had 1 master node, 6 worker nodes, 1 executor per node, and he had 3 different parameters for the number of executor cores that are assigned to each worker thread. And this is the amount of memory that could be assigned to each thread. These are the other 2 parameters for the shuffle location as well as the input storage. So with those different parameters, he came up with these 11 configurations that he tried. He started with the first configuration, number 1, and this is what he's calling the out-of-the-box configuration with these parameters for those, with these values for those parameters. And so when he started out of the box, his runtime in minutes was about 40 minutes. And by the time he ended his tuning, he took it down to about 18 minutes. And so this is the process that he went through. Of the many things that he tried in terms of the executor cores and the GC options, he found that the most significant impact was by tuning the GC options, the number of threads that he's allocating to the garbage collector. And when he took that a little further, the shuffle manager tungsten sort, which is now default in Spark 2.0, is the next thing which affected the most in terms of the runtime improvement. Now, this is another schematic view of the differences in the runtime. And without garbage collection tuning, this is where you are. And this is the amount of garbage collection time that it took in the out-of-the-box configurations. And then with the garbage collection tuning, he dropped that down significantly, 21 seconds. And then with using the tungsten start parameter, he took it down to 18 minutes, sorry. And these were the main configurations that he's recommending at the end of his analysis. And this is the impact of the garbage collection time, and down to about 16 seconds in the final configuration. And so, the analysis of that last stage, which is the most time-consuming stage, he finds that the garbage collection time so this is the duration of that garbage collection time in the default configuration, 8.1 minutes, and the garbage collection time is about 1.2 minutes from that. And in the most optimal configuration, he finds the duration of that stage was 38 seconds, down from 8.1 minutes, and the biggest impact in that was from the garbage collection time, which came down to 11 seconds. And this is why. So when he monitored it, he found that in the default configuration, he saw that the memory usage was hitting the roof pretty much very soon into the job run. And the CPU was remaining idle, but the worker threads were actually using the maximum amount of memory that was available to them. And so when he tuned that to the best configuration for the garbage collector threads, he found that the memory utilization was not hitting the peak right at the beginning. It was slowly increasing over time, and that was what was allowing the process to progress much faster. So in summary, and one of the things that I did not mention enough here is that, let me go back here. So the garbage collection thread count, the value that he found for the good enough performance of 40 threads in the garbage collector and 40 threads allocated to the Spark, 40 cores allocated to the Spark executors, these numbers are coming from by taking into consideration the number of hardware threads that are available in the system. And in the Power 8 system, there are by default there are 10 cores configured, and each core has 8 hardware threads. So in all, there are 10 times 8, 80 hardware threads, each of which appear as a core in Spark. So by dividing those 80 hardware threads equally between the Spark executors and the garbage collectors, he's able to get the most optimal performance for this particular workload. So he has taken into consideration the unique characteristic of the processor, the Power 8 processor, in coming up with this the configuration that gives him the most optimal performance. So in summary, so he's suggesting that you start by classifying the workloads. Not all workloads are CPU bound. Some are memory and IO bound. And so for a CPU bound workload, you have to first characterize what is the baseline out of the box workload performance. And then you have to take into account how much resources you have in the cluster. What is your hardware characteristic that is unique to your resources that are available for the Spark job. And then you start tuning that out-of-the-box workload and slowly navigate from the out-of-the-box point to the roofline performance point by tuning all those parameters. And if the workload is network bound, then you also have to take into consideration what he's calling the operational intensity, which is how do you give enough work to the processors by making sure that your I/O is done in a less intensive way. And there are other parameters that can be tuned for that, which we are not covering in this particular part of the presentation. But in the next part, Animesh is going to talk to you about how the network can impact the performance of the workload as well. So I/O optimizations, Animesh.
Thank you, Indrajit. So I'm going to walk you through exactly what type of impact network optimization can have on your Spark job. And we started the investigation how I/O is managed in the big data systems, what kind of impact, let's say usually, because that's the case when your job is running slower, you say, let's upgrade the hardware, right? Let's move from 1 gig to 10 gig. If you have 10 gig, then you say, let's move to 40 gig, right? So we want to understand exactly what type of gains can you expect when you're trying to upgrade your hardware with the current big data software stack, right? So here's a chart which shows you, oh, sorry, the lines are a bit off here. So here on the x-axis, we have a bunch of big data systems that we tried. So we did the Spark TerraSort. We ran PageRank, which is a very popular graph algorithm. We ran SQL Query, TPC-DS in Spark. We ran Flink, which is another very popular open source data processing system, and PageRank in that. Then we have a Graph Lab. And on the y-axis, we have the runtime these system took. So the key message here is that when we ran this system on an identical cluster setup, right, the only difference was the networking. So we ran it on 1 gig, 10 gig, and 40 gig. So these are the performance gains that we found out, right? So when you upgrade from 1 to 10 gig, obviously all of them showed performance gains, with the exception of here, but that's an anomaly. But when you move from 10 to 40 gig, essentially the performance remains flat. And that was our starting point of the investigation, exactly what is happening and how popular big data system, and specifically Spark, is managing their I/O. Why isn't getting faster with the hardware? And in our investigation, what we have found was that you do have all the emerging hardware accelerator and great performance at the bottom of the stack. But as you add gradually more layer, right, so you are running probably within a container and a virtualized system with a kernel, then you have a JVM, then you have some sort of data management layer, which is usually HDFS. Then on top of that, you might have some caching solution, which probably Tachyon, which is renamed Alluxio these days. Then you have a data processing, and at the top, you have application, essentially what's running, right? And the data that comes at the very bottom, it might be coming at 100 gig per second at the full speed. By the time it funnels through all the way to the top, you have to do multiple data copies. There are context switches, cache pollution, deep call stacks, and essentially you lose all the performance that the raw hardware was offering you at the bottom by the time it gets to the top. And this is the key reason why we didn't see any gains between 10 and 40 gig. And this type of behavior is actually also valid when you upgrade your storage, right? When you move from hard disk to SSD or SSD to, let's say, next generation of phase change memory, 3D XP point, and those kind of things, we also see similar behavior. So what are we doing about it? So in order to address this concern, and specifically the general problem that data flow orchestration in a large cluster is a first-class problem, especially the kind of diverse hardware that we have, we need to have some sort of general purpose solution. How do we manage I/O within a cluster, right? And for that, to solve that problem, we at IBM have come up with something what we call the Crail architecture. It is an open source project, and you can go to the link www.crail.io to find more details. It is meant to act as you can imagine as a high performance I/O bus going through your cluster where you can push and pull data at the speed of hardware. It is built on top of the user level I/O principles. Some of you who are familiar, it uses RDMA technology, it uses user space I/O, it uses NVMe over Fabric, and all the I/O concern essentially that you have, like how the I/O should be packaged, scheduled, how the buffer should be managed, when it's issued, when it's collected, garbage collection, everything is managed within the Crail architecture that we do. The core of the Crail architecture is a Crail store, which is a distributed shared data store, and which supports multiple type of networking technologies and multiple type of storage. You can integrate your GPUs, flash, RAM, flash storage, NVMe, various times. These are all modules within the Crail store. You can put them in. And it doesn't require overall any changes to your compute processing framework, right? So for example, on top of the Crail store, we have developed specific plugins for the shuffle operation in Spark, the broadcast operation in Spark. It also has an HDFS module, which gives an illusion that you're trying to read and write files from the HDFS. You don't need any change for that. And it's meant to provide essentially a high performance I/O bus in your cluster. It's not meant for storing your data permanently for years to come. It's meant to give you data at the speed of hardware when it's most needed. And the value of the data is when it's recent, right? You want to get your data across the cluster at the rate of 100 gig and few microseconds, not days and minutes. Okay, so what impact does using Crail technology can have on your workload? So here's an example of a workload which is a TerraSort, which is a very popular benchmark that is used which is used to evaluate the performance of a cloud infrastructure. The interesting thing about the TerraSort benchmark is that it requires you to read data from storage, process it, cross it over the network, and write it over back to the storage. So essentially, all the performance of storage, performance of CPU, performance of network comes into the play. There's no way around it. You have to be kind of optimal in all these three. Essentially, you have to be optimal across all the platform. So here's on the x-axis, this is the performance of the vanilla Spark when we run on that cluster. This was in one of the largest installation of open power systems that we have. It was 512 nodes, but we got a slice for 128 nodes. This is the configuration, and we ran 12.8 terabyte of data set for sorting. And once we moved to the Crail technology, essentially we try to use the Crail shuffler and the I/O optimization that we have. We managed to reduce the performance by almost 6x. And how did we do that? This essentially can be traced back to the original graph that I showed you. The 6x essentially is the 6x performance jump in the networking performance. Here is the network profile of this vanilla Spark, which doesn't go beyond 10 gigabit per second. It kind of peaks around here, right? When we use Crail, it jumps all the way to 70 gigabit per second. And you can see these dots here, which represents what was the network throughput that was experienced by every Spark job that the Spark scheduled for the sorting. And this is essentially in a cluster where all 128 nodes are talking to each other at the full capacity, and each of them are getting 70 gigabits per second network bandwidth. Here's the CPU profile. You can see that we were almost done by doing computation and sorting by the mark 100 second, and vanilla goes all the way up to 550 seconds for doing sorting. And just to give you an idea exactly where we stand in terms of the sorting performance, here are the numbers of this year's winner, essentially. So the winner here in 2016 used 512 node cluster, and if you calculate all the way down here, that the rate of sorting that they had was 4.4 gigabytes per core per minute. This is the sorting rate of the winner of the TerraSort benchmark this year, which is a native application written in C just to do sorting, nothing else. And in comparison, we use Spark and Crail to do sorting, which is a general purpose system written in Java. And we managed to derive 3.13 gigabytes per minute per core bandwidth, sorting bandwidth, which is pretty close to what the winner of the current world record holder of the sorting benchmark is. And here are also number in comparison what the performance efficiency of the Spark was. And Spark also won this benchmark in 2014, and how was back then. And with that, essentially, this is kind of a big picture exactly how we see Spark standing in the current distribution of Hortonworks, which was announced yesterday that it's available on the power system. So these are at the bottom you have permanent storage, then you have resource manager, you have compute frameworks, and at the top you have user interfaces. And we see kind of a parallel Crail bus going across the whole stack where you can push-pull data from each layer. Maybe it will be RPCs or broadcast or shuffle data, caching, key value stores, and they will go through the Crail fabric at the speed, the maximum speed allowed by the hardware. And the idea essentially here is that how you manage your accelerator and hardware, that should be a first-class citizen in your cluster. And we managed to, or we hope to deliver the best performance that's possible on our platform. And with that, I'll give back to Indrajit to wrap it up and tell you what Power has to offer.
All right, thank you very much, Anil. So in conclusion, I just wanted to give one slide where we summarize all the different parts of the system and all the different partners that we are working with in the Open Power Consortium to give the most, the most innovative and thing that's happening in the open power community in the hardware space. So first off, to start with, in the networking space, we partner with Mellanox, and their accelerated networking components are going from PCI Gen 3 to utilizing CAPI in the open power ecosystem to this ConnectX 5, the next generation that's coming in 2017 for RDMA InfiniBand-based networking. For the coprocessor GPU space, our partner, we're working with NVIDIA there, and they're moving from the Kepler versions of the GPUs to what is currently available, the Pascal, the P100 GPUs, and then they're moving into the Volt architecture in 2017, which has enhanced NVLink support in the open power systems. In the CPU space, from the IBM Power 8 team, we started with Power 8 in 2015, and we announced Power 8 with NVLink in 2016, and we are moving into the Power 9 architecture sometime this year in 2017. And these are the systems that we are building in the open power space. This is a screenshot of the Minsky system, and we are building more systems like this, and they're selling very, very fast. And so with that, I'd like to thank you for coming to our presentation and open it up for questions. Actually, time is up, but very quickly, one question, please.
I only want to know which is the version of Spark you used for the benchmarking of the parameters.
You know, I might have to take that back to Raj, but I think he used Spark 2.0.
So the thing is, I want to know, you mentioned the shuffle manager, the option that best performance gave you is changing to tungsten.
Yes.
And you said it's default parameter right now. And I wanted to know in which version that happens.
It happened between 1.6 and 2.0.
All right.
So it was a separate shuffler. So in 1.6 they had hash, sort, and experimental tungsten, and in 2.0 they removed all of that. It's just a sort-based
so
tungsten.
If I have 1.6, I can use tungsten in an experimental way.
Yes, I think so.